Welcome to General Relativity Lecture 1, in which I start by recapitulating and reviewing some of the concepts and notation in special relativity. What is special relativity? It is a theory that was developed by Albert Einstein in 1905. It's based on two postulates. These results that come out from these fairly straightforward postulates are very non-trivial, and there are things such as the time dilation and length contraction that are based entirely on theory. Nevertheless, this theory has been experimentally tested very well, and it sort of has passed all the tests that have been conducted in the intervening 115 years. In the current lecture, I will only be able to give a very brief review of special relativity. Basically, I will assume that you already have mastery of special relativity from some prior course in order for us to get started into the actual meat of the course, which is general relativity. Here I will only review some of the basics of special relativity, and I will do this mostly with an eye towards setting up general relativity. To get started, just consider a very classical physics example. You have two students, or a student and a student TA. The student is on a train that's moving with velocity v train in our picture to the right. And the student's TA is on the ground and he's firm on the ground, so he's not moving. The student on the train has a ball, which he's throwing in the direction of the train. And then from the student TA's perspective, the ball's velocity that he sees will be the velocity of the ball that the student is throwing on the train plus the velocity of the train. So basically you get an addition of the velocities, which is the velocity that the student's TA will see. It's a fairly straightforward example. However, there is some interesting twist to the story when we consider special relativity. So if you consider the motion of the Earth around the sun, then we could try to figure out our relative velocity with respect to some sort of reference frame, which back then was called the luminiferous ether. And the idea is simply that if we have a certain measurement, let's say in the spring, then we would basically measure the velocity with respect to the direction where the Earth is, for instance, moving against the position in the ether, and half a year later in the fall, that direction would be reversed and we would be moving in the other direction. So if the situation was akin to what we have for the ball on the train, we would in this case measure the difference between the two velocities, so the Earth with respect to the ether, and in this case we would measure the sum of the two velocities. In any case, we expect the velocity difference to change as a function of time when the Earth goes around the sun. So that was the idea. Try to measure the velocity of the Earth relative to the ether. And in the late 19th century, in 1887, Michelson-Moreley set out to do precisely that, measure the Earth's speed with respect to the ether. They knew they needed a very precise tool to do this. And one of the most precise tools that they had available, actually that we still have available, is a light interferometer. I will not go into the details, but basically it involves having some sort of interference pattern that you expect to change as you change the velocity relative to your emitting source. The upshot of the experiment was that it failed. They couldn't detect any velocity at all, and this really was a shock to the physics community. There were some contortions where people were trying to come up with conspiracy theories, how it's possible that some kind of demon masked the velocity of the Earth through some technical mechanism. And really, for a few years after the experiment, there was really sort of a turmoil in the physics community. Enter Albert Einstein. Albert was born in 1879 in Ulm in Germany. There's a picture of him at age 14. He was a math prodigy, and he got his teaching degree from the ETH Zurich in Switzerland in 1900. He didn't find a job as a teacher, so he took a job at the patent office in Bern reviewing patents, and he seems to have reasonably enjoyed that job because it allowed him to work on his physics theories on the side. As part of this side job that he sort of took by taking time off from his actual job, he published 4 groundbreaking papers in the same year, in 1905, and he got a PhD based on the sort of brilliance of these papers in the same year. He later emigrated to the US, namely in 1933, and then was famous for being the head of the Institute of Advanced Studies in Princeton. So what did Einstein do in one of these brilliant papers, in the special relativity papers? So he sort of came up with 2 postulates, 2, if you want, so assumptions or statements about nature, and he used these to set up his theory of special relativity. One of the postulates in this theory is that the speed of light is constant, and that the laws of nature are independent from the translational motion and rotations. So basically, this is saying that the laws of physics shouldn't change whether you're at standstill or whether you're moving on a train. The laws of physics should be independent of this. An important consequence of these 2 postulates was that there could not be any preferred theorem. So basically, Einstein's sort of postulates directly led to a conclusion that there is no ether. So in this sense, it naturally explains the failure of the Michelson-Moreley experiment, who were trying to find Earth velocity with respect to this ether. It so happens that special relativity today provides the formal framework for modern high-energy physics. So it's the same setup in slightly different notation that Albert Einstein came up more than 100 years ago. There are some important consequences except for explaining things like the Michelson-Morley experiment. So for instance, there are consequences such as the delay of time for fastly moving objects, the contraction of length for fast-moving objects, and that space and time cannot be treated separately, but must be treated together. Usually, we are often sort of using vectors in 3 space-time dimensions. So we call these 3 vectors, and I'll label this with a little arrow here. So x vector basically would be the combination of x, y, z. We can also use index notation for these vectors. So instead of writing x vector, we can also write xi, where I goes to 1, 2, 3, and then x1 is identified with x here, x2 with y, and x3 with z. If we are to treat space and time as one entity, we are then led to consider so-called 4 vectors that lump together space as a vector and time. And we sort of write these together as a 4 vector, which we denote as x mu with Greek indices. And where c here is the speed of light in vacuum, such that all entries of x mu have the same dimensions. We use, as I said, Greek indices for the 4 vectors, and these Greek indices, for instance, mu, then run from 0 all the way to 3. This is opposed to the Latin indices that I use for 3 vectors, which run only from 1 to 3. So the 0 component of these will always be the time-like direction. Let's now consider Lorentz transformations. If we have 2 different coordinate systems with coordinates x and x prime, and we assume that these 2 coordinate systems coincide initially at time 0 at their initial or origin of these 2 spacetimes is the same. And if we then consider that these 2 initial frames are moving with a relative constant velocity v in the z direction, then because there's no movement in directions x and y, we find that the coordinates between these two systems, x and x prime, must be related such that the two coordinates in which there is no movement, x and y, are unchanged. So x prime and y prime must be equal to their corresponding unprimed coordinates. The distance of light traveled in both frames then obeys the following relation. So the distance in the unprimed frame is just the total sort of sum of the coordinates squared. And this is equal to the speed of light squared times the time squared that light is allowed to sort of travel. And if we take the idea that this length is measurable in both coordinate systems, it must be the same in the primed system, where it's the sum over the primed coordinates squared. And this is equal to the speed of light in the primed system squared times the time in the primed system squared. Now, one of the postulates of special relativity is that the speed of light in the prime system, the one that is moving, if you want so, is the same as the speed of light in the non-moving frame. So c prime, the speed of light in the prime system, is equal to c. If the distances L and L prime are then the same, then we can simplify these two relations by sort of bringing the time squared terms on the respective left-hand side. And the equation that we have then gives us an equation that relates the unprimed coordinates and the primed coordinates. If we, in addition, use the relation that the x and y coordinates are unchanged, so they're the same in the primed and the unprimed frame, then basically we have a relation that just relates the time and z coordinates in the unprimed and primed coordinate system. Since we have a constant velocity, we expect that the relation between the unprimed and the primed coordinates is linear. And the way we sort of set this up is that we say the prime coordinate system is a constant a times z minus vt. And the primed time t prime is a linear combination of time and z in the unprimed frame, where a, b, and d are all constants. So then we have three unknowns, a, b, and d, and we have three equations, 1.3 and 1.4. We can solve for these three unknowns from the three equations, and that will be one of the homework problems. We find that the corresponding transformation laws then take a, if you want, a surprisingly complicated form. There are square roots appearing and things like that, but it nevertheless is a linear relation between the primed and the unprimed coordinates, even though it's not linear in the velocity. If the velocity, you see that there are these squared appearing where we have the velocity squared of the speed of light squared. If the velocity is much, much smaller than the speed of light, then you can approximate the square roots in particular by 1, and then you get transformations laws that would be conforming to, for instance, our exercise with the ball on the train. But for velocities that approach the speed of light, the changes to these coordinate transformations become substantial. And that's basically where the special relativity sort of framework really becomes very powerful. It's customary to introduce abbreviations such as beta for the ratio between the velocity and the speed of light, and gamma for 1 over the square root of 1 minus beta squared, such that these transformation laws here are simpler to write. We just get z prime is gamma times z minus beta zt, and zt prime is gamma times ct minus beta z. These transformation rules that I just derived are examples of so-called Lorentz transformations. Lorentz transformations are transformations for systems that move with respect to each other by some constant velocity. In our example, that velocity was pointed in the z direction, but we can have more general movements such that the velocity is not in z but in x, or some combination of x, y, and z. And in addition, we can also consider rotations. All of these together make up possible Lorentz transformations. In the example we had, where the velocity is in the z direction, the transformation laws that I just wrote down in the previous slide can be written in matrix form. So if we write our 4-vector in the prime coordinate system, ct prime, x prime, y prime, z prime, and the coordinates in the unprimed system, ct, x, y, and z, then we can write all of the transformation rules using one big matrix where we have these gammas and betas appearing. Note that this is nothing else but our 4-vector x prime with a 4-index mu. This is our 4-vector x nu. So we can write this matrix multiplication by just naming this transformation matrix lambda mu, which now has 2 indices. So basically that's a rank 2 matrix. It must have 2 indices to specify all the entries of this. And then if we recognize this lambda to be the so-called Lorentz transformation matrix, our transformation rule becomes very simple. It just says that x prime mu is the sum over all entries of nu from 0 to 3 of this transformation matrix lambda and the unprimed coordinates x nu. Note that in this case, using this matrix multiplication, the matrix multiplication simply is expressed by the fact that we are summing over 1 over the indices, in this case nu. And if you have never sort of dealt with index notation before, I think it's a good exercise to check that this is indeed giving you the transformation laws that we had in this equations 1.7 here. The matrix multiplication in index notation is an extremely compact notation, so we don't have to write very much. We can try to be even more efficient and omit also the summing symbol from this expression. The omission of the sum symbol is known as the Einstein sum convention, which says that whenever you see an index that's repeated twice, this index is to be summed over. So in here we have the index nu that's appearing twice. It's summed over all its values, but because it's appearing twice, we already know that we have to sum over it. So basically, for this particular case here, Einstein sum convention simply allows us to write this expression as x prime mu is lambda mu nu x nu, where the sum over nu is implicit through the fact that the index nu is appearing twice. So this is our first start into the review of special relativity, and in the next lectures, we will continue this review, setting up more and more of the notation that we need in order to get to general relativity. And this concludes the lecture.